Let's take a look at this example. Please notice that this circuit has 4 nodes. This is my reference node, okay? The node which is connected to the ground. And this is my node V1, this is my V2, and this is my node V3. Please notice that we are going to have 3 equations, okay? Because total number of nodes with 1, 2, 3, 4 minus 1 gives me the number of equations needed to solve the values of V1, V2, and V3. Okay, so next we're supposed to simply find the impedance, okay, or we can say resistance of these 2 resistors together. Okay, I'm going to call the total resistance of these 2 Z2. Okay, why? Because this is going to be my Y1, this has to be my Y2, and this is going to be my Y3. So this is going to be my Y4. That's why I'm going to call total resistance of these 2 resistors Z4, and I'm going to call this admittance Y5, and this is going to be my Y6. Okay, so let's find Z2 and Z4 first. Z2 is equal simply the total impedance or total resistance of these 2 resistors. So I have R2 plus R3, where R2 is equal 2 kilo ohms plus 3 kilo ohms is equal 5 kilo ohms. Okay, remember, you must write the formula first. After that, you're supposed to plug in the numbers and write the answer. Next, we're supposed to write formula for Z4. Z4 is equal R5 plus R6, and this is equal 1 kilo plus 3 kilo, and this is equal 4 kilo ohms. Okay, so now we can start finding our admittances. So we have Y1 is equal 1 over R1 in this case. So this is equal 1 divided by 1 kilo ohm is equal 1 millisiemens. Okay, this is my Y1. Next, I'm supposed to find Y2. Y2 is 1 over my Z2. We found the total resistance of these 2 resistors, and we found that this is equal 5 kilo ohms. So this is equal 1 over 5 kilo, and this is equal 200 microsiemens. Next, I'm supposed to find Y3. Y3 is 1 over R4. Okay, so this is equal 1 divided by 2 kilo. This is equal 500 microsiemens. Next, I'm supposed to find Y4. Y4 is the simply 1 divided by Z4, and this is equal 1 divided by Z4 is equal 4 kilo ohms. So 4K, 250 microsiemens. Okay, so next I'm supposed to find Y5. This is equal 1 divided by R7, and this is equal 1 divided by 2 kilo ohms, which is equal 500 microsiemens. Next, I'm supposed to find Y6. y6 is equal 1 over r8, and this is equal 1 divided by 5 coulombs, and this is equal 200 microsiemens. Okay, so next we're supposed to find the currents, right, which are going to come or leave the particular nodes. I mean V1, V2, or V3, and V3 I'm supposed to say. So now let me write the formula first. Sum of the currents going to or leaving node 1. This is equal. Please notice that current source I1 is connected to node 1, and current source I2 is also connected to node 1. But the current of I1 is going to the node, and current I2 is leaving the node. That's why I1 is going to be positive, and I2 is going to be my negative current. That's why I'm going to write over here I1 positive minus I2, and this is equal 5 milliamps minus 7 milliamps is equal negative 2 milliamps. Okay, so next I'm supposed to find the sum of the currents at node 2. So please notice that only one current source is connected to node 2, my current source I2, and the current is coming to the node. That's why this is going to be positive current. That's why I'm going to write over here I2. I2 is equal 7 milliamps. Next we're supposed to find the sum of the currents at node 3. Please notice that only one current source, I3, is connected to node 3, and the current is leaving the node. That's why this is going to be my negative current, negative I3, and this is equal negative 10 milliamps. Okay, so now we're supposed to find Y11, where Y11 is simply the sum of the admittances connected to node 1. Okay, so I mean I have to add Y1 to Y2 and add to Y3. So this is equal Y1 plus Y2 plus Y3. Y1 we found is equal 1 millisiemens, so I have 1 millisiemens, plus Y2, which is equal 200 microsiemens, plus Y3, which is equal 500 microsiemens. Okay, if you are going to add them up, you are going to end up with 1.7 millisiemens. Okay, so this is my Y11. Next, I'm supposed to find Y12, which is equal to Y21. This is the admittance between node 1 and node 2, or admittance between node 2 and node 1. And this is equal to Y3. So Y3 we found is equal 500 microsiemens. Next, we're supposed to find Y22. Y22 is the sum of the admittances connected to node 2. So this is Y3 plus Y4 plus Y5, because all of them are connected to this point. So I have Y3 plus Y4 plus Y5. So Y3 we found is equal 500 microsiemens plus Y4, which is equal over here 250 microsiemens plus Y5, which is equal 500 microsiemens, and this is equal 1.25 millisiemens. Siemens. Okay. Next, I'm supposed to find Y23, which is equal Y32. Okay, so this is the admittance between the node 2 and node 3, or between the node 3 and node 2. This is equal to Y5. So Fy5 over here. And Y5 we found is equal 500 microsiemens. Okay, next I'm supposed to find Y33. This is the sum of the admittances connected to node 3. Okay, so we have Y5 plus Y6 because these two admittances are connected to this point, which is called my node 3. Okay, so I have Y5 plus Y6. Y5 is equal 500 microsiemens plus Y6, which is equal 200 microsiemens. This is equal 700 microsiemens. Next, I'm supposed to find Y13, which is equal Y31. Please notice that there is no any direct connection between node 1 and node 3. Okay, because between we have node 2, so there is no such a thing like extra resistor going from point V1 to V3. That's why I'm going to say that this is equal 0 Siemens. Next, we're supposed to write the general formula for the 3-node circuit. Okay, so the formula says Y11 V1 minus Y12 V2 minus Y13 V3 is equal sum of the currents, okay, at node 1. Next, you're supposed to write negative Y21 V1 plus Y22 V2 minus Y23 V3 is equal sum of the currents at node 2. Negative Y31 V1 negative Y32 V2 plus Y33 V3 is equal sum of the currents at node 3. Okay, so this is my formula. Many students have difficulties to remember these three formulas, okay, because they got confused where they're supposed to write 1, 1, 2, 1, and so on, so on. You have to keep in mind that the first digit represents the row. The second one represents the column. So I have first row, first column. First row, second column. First row, third column. Okay, this is second row, first column. Second row, second column. Second row, third column. And please notice that the positive, okay, positive admittances, okay, the positive coefficients of V's, right, V1, V2, and V3 are only the ones which have like digits, okay, with the same digits. I have 1, 1, 2, 2, and 3, 3. Rest of them are negative. So this is very easy to remember. Now we are going to substitute the variables by the numbers. Okay, we have, if you are going to look at the formula, we are going to see first Y11. So Y11 we found is equal 1.7 millisiemens. Next, I'm supposed to copy down from the formula V1 minus Y12, which is equal 500 microsiemens, and I have V2 minus Y13, which is equal 0 Siemens, V3, and the sum of the currents at node 1, which is equal -2 milliamps. Okay, this is my first nodal equation. Okay, in many problems you are going to find the question called, let's say, write the nodal equations. Okay, so this is how the nodal equation is supposed to look like. In this case, we are going to have 3 of them. So next, we're supposed to write the negative sign, like you see in the formula. So I have negative y21. Okay, so I have negative 500 microsiemens V1. Next, if you are going to look at the formula, you will see plus y22, which is equal 1.25 millisiemens. Okay, this is millisiemens. And I have V2, and I have minus y23, which is equal 500 microsiemens V3. Okay, this is my 3, and this is equal sum of the currents at node 2, which is equal 7 milliamps. Okay, this is my second nodal equation, and I'm supposed to find the third one. So I have negative sign, and I have y31, which is equal 0 Siemens V1, minus y32, which is equal 500 microsiemens V2, plus y33, which is equal 700 microsiemens V3, and this is equal sum of the currents at node 3, which is equal -10 milliamps. Okay, so we got 3 nodal equations. Now I'm going to use the calculator to solve these 3 nodal equations, but you're supposed to realize that these are nothing else, just the linear equations. So if you are going to set your calculator to solve the linear equations, 3 linear equations, your calculator is going to give you the answer right away. If you want to do this manually, you're supposed to use, for example, determinants to solve the values of V1, V2, and V3. I'm going to use the calculator. So I have mode 2, 1, and I have 1.7 exponent 3 negative, press equal, 500 negative exponent 6 negative, and I have 0, and I have -2 exponent 3 negative. Okay, next I have 500 negative exponent 6 negative, and I have 1.25 exponent 3 negative, and I have 500 negative exponent 6 negative, and I have 7 exponent 3 negative. Next I have 0, and I have 500 negative exponent 6 negative over here, and I have positive 700 exponent 6 negative, and I have 10 negative exponent 3 negative, and I got the answers. My V1 is equal 1.46 volts negative. Okay, so this is my V1. I'm going to write this over here. V1 is equal negative 1.46 volts. Okay, next I have my V2. V2 is equal negative 980.28 millivolts, and I have also V3, which is equal negative 14.98 volts. Okay, I found the voltages. okay, at my circuit. So next we're supposed to find the voltage VR3, and we're supposed to find the current and also the powers. Okay, so let's take a look what we're supposed to find. We're supposed to find VR3. Okay, VR3 is the voltage at resistor R3. Okay, please notice that these two resistors are in series. We've found already voltage V1. Okay, V1 is the voltage between this point and ground. So if you want to find the voltage across this resistor, we can use Ohm's law, or we can use simply voltage division law. Okay, if I'm going to multiply this voltage by this resistance and divide by total resistance of these two, I'm going to find the voltage across this resistor. Okay, so I'm going to use voltage division law. So I'm going to write that VR3 is equal V1 times R3 over, I'm going to write Z2. Why Z2? Because we said that the total resistance of these two resistors I'm going to call Z2. Okay, and we found that Z2 is equal 5 kilo ohms. So I have V1, we found is negative 1.46 volts times R3, which is equal 3 kilo ohms, over Z2 we found is equal 5 kilo ohms. Okay, so VR3 is equal, now I'm going to use the calculator to find VR3, so I have 1.46 negative times 3 exponent 3 divided by 5 exponent 3. This is equal negative 876 millivolts. Okay, so this is my voltage VR3, which is the voltage across resistor R3. Okay, next I'm supposed to find the current which goes through resistor R7. Okay, so this is the current which will go through this resistor. So if you want to find the current, you're supposed to find the voltage across this resistor. Voltage across this resistor is the difference of these two voltages. So I can say that the formula for IR7 is equal V2 minus V3 over R7, where V2 we found is equal negative 980.28 millivolts. This is equal this, okay, minus V3, which is equal negative 14.98 volts, okay, over R7. R7 is equal 2 kilo ohms. Okay, so now we can use the calculator. So we have negative 980.28 exponent 3 negative. Negative times negative will give me positive, plus 14.98 equals, divide by 2 exponent 3 is equal 7 milliamps. Okay, so the current which will go through resistor R7 is equal 7 milliamps. And someone is going to ask in which direction this current is going to flow. Okay, please notice that V2 is equal negative 980.28 millivolts, and V3 has value of negative 14.98 volts. And keep in mind that we use the nodal analysis, so the higher potential is at V2 and the lower potential is at V3. So if we use the conventional current flow, we say that the current flows from the higher potential to the lower. So current will go in this direction from V2 to V3. Okay. Next, we're supposed to find the power at resistor R1. Okay, voltage across resistor R1 is equal to V1. Okay, because V1 is the voltage between this node and ground, so this is also the voltage across resistor R1. That's why I'm going to write the formula P R1 is equal V1 to the second power over R1, where V1 we found is equal negative 1.46 volts to the second power over R1, 1 kilo, and this is equal 1.46 negative raised to the second power divided by 1 exponent 3. This is equal 2.13 milliwatts. So this is 2.13 milliwatts. Okay, so this is the power at resistor R1. Okay, so this is my R1. Next, I'm supposed to find PR8. Okay, the power at resistor R8. Very similar situation. Voltage V3 is the voltage across this resistor. V3 is the voltage between this point and ground. And this is also voltage across resistor R8. That's why I'm going to write that PR8 is equal V3 to the second power over R8. So I have V3 we found is equal negative 14.98 volts raised to the second power over R8, which is equal 5 kilohms. This is equal 14.98 negative raised to the second power divided by 5 exponent 3. This is equal 44.88 milliwatts. 44.88 milliwatts. Okay, and at this moment we can say that the problem is solved.